All right, I do the things in a little different order than the book. We just did finding high points and low points in section 4.1, and so I like to move right into section 4.7 right away, which is called optimization. Optimization is trying to get the most out of something, or use the least amount of material, or somehow maximizing or minimizing. And so let's use the stuff we just learned in 4.1 to solve some application type problems. Okay, there's a lot of different problems. They're similar in the setup. They're of course different in each of the situations, but the idea is the same, as we'll see over. I'll do 4 or 5 examples here over the next few videos. Let's start with this one. The farmer's got 1,000 feet of fence to enclose a rectangular field. One side of the field is along a straight river, so no fence is needed on that side. He's probably herding, trying to keep in cats or something. He knows they won't swim out in the river. Anyway, find the dimensions of the field if the farmer wants to enclose the largest possible area. Okay, so we got the river on one side, and it's a rectangular field, so there's going to be fence on the other sides. Okay. Now, a couple things I notice. One is it says you want to enclose the largest possible area. And in any of these optimization problems, you establish what's called the objective function. What is the thing you're trying to get the most out of, or the least from? In this case, we want the most possible area, the largest possible area. So my objective function is area, and I need area equals something. Okay. If it had said, he needs 1,000 he needs 1,000 square feet, how much fence would he need? What's the minimum length of fence? Well, then the question is minimum length of fence. So length equals, establish what's trying to be maximized or minimized. In this case, it's area. Now I need to say, what are my variables? What are the things that can change? So I'm picturing this, there's a fixed length of fence here, 1,000 feet. But that 1,000 feet could be, put to use several different ways. You could have, kind of a really short distance away from the river, and then really long fence this way, and then back over there. Or maybe it's more like this, or anything in between. Like there's all these different arrangements where you add up those 3 sides. They got to add up to the 1,000 feet. And there's all different amounts of area depending on which one we have there. So what are my variables? What are the things that can change in this thing? Well, I'm going to erase a bunch of this stuff just so that I'm only looking at one. There we go. That looks a little better. Well, the side lengths, it can change. Let's call this X and that Y, or maybe the other way around if you like. That doesn't make any difference. This one's also going to be X. Well, the area of that rectangle is going to be X times Y. Okay. So I've established my objective function, area. I've established the things in the problem that change, that I can vary. I can vary those side lengths. Right? Before I can actually solve this now, though, I need to get this down to just a single variable here. Area is a function of X and Y, but there must be some relationship between X and Y that I can use to get rid of one of these variables. And that relationship is that there's 1,000 feet of fence. I haven't used that information yet. So I know that 2x plus y is equal to 1,000. So solving for either one of the variables, let's solve for y. Here y is 1,000 minus 2x. And I'm just going to plug that in here. So what I have is the area is x times 1,000 minus 2x. Okay. So now the area is what I'm trying to maximize. My variable is x. I have a as a function of x. There are a couple of restrictions on x that I should point out. X could be as small as 0, and it could be as big as, I think, 500. So to have x equals 0, you'd have it, essentially no distance from the river, all the 1,000 feet this way, and then 0 back. Or the other is to have all 500 feet coming out this way, 500 feet going back, that way. I think in either of those two cases, you can see that I'm getting minimum amount of area. That's area 0. But I need to be aware of those endpoints, because where can maximums and minimums happen? They can happen at critical points. They can happen at endpoints. Well, here's my endpoints. My endpoints are going to give me minimum area, 0. Right? So somewhere in the middle, I'm going to be able to find a maximum. Actually, if you think about this, this function, this is a parabola. In fact, I can probably do this without any calculus, because I can see that this is a quadratic function of x. I've already got it factored. So the first factor tells me there's a 0 at x equals 0, and the other one is out at 500. Oh, no kidding. At 500, we just established that. And this is a parabola that opens downward. And so somewhere in the middle is going to be a maximum. In fact, I think I can say that the maximum happens at 250. Parabolas here, quadratic functions, are symmetric about the vertex. So anyway, I'm going to do the calculus anyway, but I already know the answer is at x equals 250. But what I would generally do here, if I couldn't just see that answer, I would multiply this out here, 1000x minus 2x squared. And I'm trying to find a maximum. Where do the maximums happen? Critical points, endpoints. So I'm going to take the derivative and see if I can find that place where the derivative is equal to 0. So dA dx is equal to 1000 minus 4x. And so this is critical if 0 is equal to 1000 minus 4x. Well, that doesn't look like a 4x, does it? Let's try that again, 4x. And so you solve for x. 4x equals 1000, x equals 250, which we know. Okay. Now, last thing that you got to do on any one of these problems is make sure you answer the question. What did they ask for? They asked for find the dimensions of the field. Dimensions of the field. So x is 250. I can calculate y here now. Y is 1000 minus 2 times 250, which would be 500. So it seems that the maximum area happens when it's twice as long as it is wide. So this is 250, this is 500, this is 250. Okay. That will maximize the area. Sometimes it might say find the maximum amount of area. Now in this case it didn't ask me that. It asked me to get these two dimensions, but the actual area then would be the product of these two, 500 times 250, whatever that is. Must be 125 with 3 zeros. So, and this is in square feet, which is I'm just thinking that's a couple of acres. Anyway, there is an optimization problem. I'm going to do a bunch more. Establish your objective function. Establish what can change, what are the variables. If you have more than one variable, there must be a relationship given somewhere so that you can use that relationship to get it down to just one variable. See if there's any endpoints, check your endpoints, check your critical points, find those maximums or minimums as the case may be. Right. There you go. There's your first optimization problem.